Okay, so covering the last section of chapter 15, solar activity and space weather. So we're going to cover a series of key terms here about events that happen on the surface of the sun that fall into the category solar activity. All of these are going to relate to the magnetic field. Okay, so every solar event has to do with the sun's magnetic field, which is a good thing to remember. That's the driving, disruption to the sun is its magnetic field and the way that it's always changing and the way that its field lines are always getting disrupted due to the variable rotation rates of the sun's surface. So plages are bright clouds of warm regions near sunspots. So it's a name given to a region above the photosphere that is particularly bright because of its high temperature. Okay, and we're kind of going in order of severity for these solar activities. Next up are prominences. These are enormous thick loops of gas, okay, a plasma because of the high temperature, an ionized gas, that are attached to the surface of the sun. So these loops of gas follow the magnetic field lines that come out of one sunspot and back into another. So you can really think of this as a magnetic field line with gas twirling around that field line and creating this structure. They last for a few days usually, Earth days, and then fall apart, sometimes dramatically, sometimes with less commotion. You can see that their size is huge, compared to the Earth. That has, of course, a lot to do with the sheer size of the sun. And they've been observed all the way back into the 12th century, flame-like tongues of live embers. So, in other words, you can observe them with naked eye observations, although without harming your eyes would be kind of tricky. But if you had a way to, probably looking at a reflection of the sun, right? So rather than looking directly at it, using some sort of mirrored surface. All right, so now a quick rundown of some other types. We've got spicules, filaments, faculae, coronal loops. All right, so these are other types of solar activities. A lot of these are mentioned in your book, all of them to some extent, except for helmet streamers. And you can look into these. They all have to do with the magnetic field. But getting into the next key solar activity or solar event, which is a type of solar activity, are solar flares and CMEs. All right, and let's see, which were not mentioned. So solar flares and CMEs are the two most high energy events that can happen on the surface of the sun. And CME stands for coronal mass ejection, which you'll see in a moment. So a solar flare is a sudden burst of X-rays when a magnetic field suddenly snaps and reorganizes. So it's a dramatic and sudden release of X-rays. So lots of high energy light makes for a bright spot on the surface of the sun. And of course, those X-rays then stream out into the solar system. A coronal mass ejection is when a burst of particles, so the same constituents as the solar wind, protons and electrons, move fast enough to escape the sun's gravitational pull. So they have been accelerated, maybe because of some sort of coronal loop, and then they get a trajectory that causes them to move out into space. So in the case of a coronal mass ejection, it's a big clump of hot gas that is moving away from the sun. And so they just head out into the solar system, dissipating as they go. But instead of it being a wave of light, it's actually a wave of matter, ionized matter. All right, some videos to look at. You can follow these links if you want to see videos of the different events. Coronal holes are windows in the corona where magnetic field lines extend out into space. So this is a view directly through the corona. And so looking at a regular sunspot magnetic field, as we saw before, coming out of one sunspot representing the north pole of the field, and then entering at another sunspot representing the south pole of that field, and the field lines connecting the poles like a big U-shaped magnet. Well, in the case of a coronal hole, the lines extend out so far that we can look right down the field lines. And from our vantage point on Earth, we have this view that is not obscured by the gas on the field lines themselves. Such events cause an increased speed and intensity of the solar wind. So coronal holes are going to cause an uptick in the solar wind, which you remember when we talked about the levels of the atmosphere, is all the solar wind is all throughout the corona, which extends well out into the solar system. So continuing with this relationship to the solar wind, well, the solar wind itself is the steady flow of electrons and protons from the sun. The coronal mass ejections are a particular uptick in that number of particles, electrons and protons coming from the sun, and both of them are going to bombard Earth. They're going to bathe Earth in charged particles. So you're going to have an incoming amount of particles. And again, the coronal mass ejection would just be an increase in intensity. So imagine just more of these white lines, right? Thicker, greater number of them would, for a particular short period of time, being associated with the CME. And of course, we know from when we talked about the Earth, the auroras, which are the northern and southern lights, are when at least on Earth, are when a planet's magnetic field moves those charged particles to the poles, where they are excited in the atmosphere and cause glowing. Jupiter has clear auroras, visible bands of excitation happening in the atmosphere of that Jovian world. And in that case, there's nice alignment between the magnetic field and the rotational axis. And if there wasn't, then it would still be the magnetic poles where the excitation occurs, even if those are not the rotational poles. Here is a picture of a so-called dragon aurora in Iceland, because it looks like a dragon, vaguely. Right? But they can be quite dramatic. The different colors correspond to different molecules in the atmosphere, or different excitation levels within a given molecule, but usually different molecules themselves. And then essentially they're glowing at different wavelengths because of that excitation, electron kicking up to a higher level, eventually relaxing back down to the ground state. And when the electron relaxes, that's when the emission happens. The emission then is what we see. That's the color. So in other words, the auroras are a type of emission spectrum. It's just an emission spectrum happening in our atmosphere, there's plenty of examples of, terrestrial emissions, like neon signs, like I like to say. Auroras in space, as we'd seen before when we talked about Earth, when we had our chapter covering Earth. Here's aurora on a visible aurora at the pole of Saturn. I said that we'd seen it on Jupiter, but we actually had not seen an image showing it on Saturn yet, so that's nice. And here is it in Eugene, which obviously I think the creator of the slides must be from there, because it's not the second time the city has been mentioned. All right. So a bit of a summary about space weather. Solar wind and coronal mass ejections send charged particles to Earth. The auroras, right, a planet's magnetic field moves them to the poles, where they excite air particles and make them glow. Well, is that it? Is it just a pretty glow? Well, not entirely. The biggest solar wind events, which you are generally going to be, a uptick because of a coronal mass ejection, or some relation to a coronal hole, are going to lead to big storms. The largest solar storm, which took place in the 20th century, was back in 1921, when it caught telegraph equipment on fire and burned down a building. How did that happen? Because the telegraph equipment acted like an antenna that picked up the energy coming in down the field lines, and essentially that antenna was able to resonate or pick up all that energy, and that caused the telegraph cables to heat up more than they were intended to do. The fastest coronal mass ejection ever recorded was in 1972 that detonated the Navy sea mines around Vietnam because of their disturbance to the transmitters on those devices. And the second largest known, which is far from polar, right? More of like an equatorial location. And obviously they were susceptible to it. The second largest solar storm in 1989 caused large regions in Canada. This is the one I know the most about, I've read about, and affected more than 6 million people in terms of loss of power for up to a day. And the effect was similar to what I had just described for the telegraph equipment, because the grid, essentially, the grid of, in this case, electrical lines acted like a antenna. So the way that the long range power lines that span big expanses of open territory, think Canada, with big open regions of forest and nothing else, and those big long distance high voltage power lines running in straight paths across the terrain. Well, it happened that those long straight paths acted to pick up the signal. They picked up that electromagnetic signal that was being created by the absorption of the solar wind. And so that means that some adjustments had to be made, not in terms of necessarily tearing down lines, but thinking about how can the grid be, changed or turned off momentarily to prevent this happening in the first place. How can we stop this sort of, effect? Or how can we even apply a voltage in a smart way to oppose the input? These are all things that we can anticipate, and as long as we're monitoring the solar wind. So since then, more close monitoring of the solar wind has really assured, despite many more electrical lines being built, even since 1989, the risk has gone down because the close monitoring means that we know how to prevent these types of large scale blackouts caused by solar storms. So we have these branches of NASA and the Internet and the European Space Agency that are actively monitoring the sun for this exact type of thing. One thing that remains risky is satellites, especially people in satellites. There is always a risk associated with human exposure, such as on the International Space Station, more than anywhere else. But also just, satellites without people in them can get damaged due to solar flares and upticks in the solar wind. And that goes with the territory and design of the satellites tries to prevent that as much as possible. And that concludes our lecture on chapter 15.